So in the last lecture, we defined a product measure on a finite product of spaces. Today we will discuss product measures on a countable product of spaces. So we will assume that we start with a measure space, so omega j, fj, and mu j are a measure space for j greater or equal to 1. And I would like to define omega as the infinite product space of omega 1, omega 2, and so on, which I will represent by the product for j greater or equal to 1 of omega j. So elements of omega, which will be represented by, say, the letter x, are in fact sequences x1, x2, and so on, where xj belongs to omega j. And we would like to define in this space omega a measure with the following property. If I take a set E of sequences where E can be written as E1 times E2 times En times omega n plus 1, omega n plus 2, and so on. So starting from some index n, all sets for n greater, for a k greater than n, are the complete sets omega. So we would like to define a sigma algebra generated by this type of set, which I will represent by f, which is the product, say, of the fj's. So we will define f as the sigma algebra generated by this type of sets, and we would like to define mu of such a set as the product from 1 up to n of mu g e j times j greater than n of mu j omega j. So in particular, you see that we'll need this product here to be well defined. And in order to avoid discussing whether this sequence converge or not, I will just assume during this talk that mu j of omega j it's equal to 1. So that these measures are in fact probability measures. So the measure of the entire space is equal to 1. So with that assumption, this is just 1, and therefore the measure of a set E1, E2, En times omega n plus 1, omega n plus 2, and so on will be just the finite product of mu j ej. So this is a goal. We start with that space, which is the space of sequences. We consider a special set or family of subsets of omega that we will call cylinder sets. We will then define the smallest sigma algebra which contains these sets. So the sigma algebra generated by these sets, which will be represented by f. We will define mu on this class by this identity, and we would like to use Carré-Theodori theorem in order to extend this measure to the sigma algebra f. So this is the goal of the lecture today. So remember, we start with measure space, omega j, fj, mu j. So a countable family of such measure space. We are assuming that the measure mu j, it's a probability measure. And so we represent by omega the product of omega j. So the space omega are formed by ordered sequences, so sequences of points in omega j. So we will represent, say, by x points in omega, and x will be a sequence x1, x2, and so on, where xj belongs to omega j. To keep notation simple, I will represent by omega n the product of omega n plus 1, and so on. So with that notation, that will be just the product for j greater or equal to n of omega j. So this is just a notation. And then I will represent by C a family of subsets of omega, which will be called the cylinder sets. And the cylinder sets are those sets. So a set E belongs to C if E can be represented as E1, E2 times E2 times En times omega n plus 1. With where omega n plus 1, remember, is just the product of all the omegas starting from n plus 1. And here I'm requiring, so I would say that a set E is a cylinder function if it can be written in this form. So if there exists n, and so I want that there exists n, and that there exists Ej, which are elements of the sigma algebra Fj for j between 1 and n, such that E can be written as E1 times E2 times En times omega n plus 1. So this is the definition of the cylinder sets. So you see the cylinder sets are essentially n-dimensional. If I give you a point x, so a sequence x1, x2, and so on, and to check whether this sequence belongs to the set E or not, I just need the value to know the value of the first n coordinates. So the sequence x will belong to E if and only if xj belongs to Ej for j between 1 and n. So I just need an information about the first n coordinates in order to check if a point belongs to a cylinder set or not. So these are essentially finite dimensional sets. So my first claim is that the set C is a semi-algebra. So that will be the starting point of the construction of the measure mu on the product space. We will define mu in this semi-algebra, and then we will extend it to the algebra and to the sigma algebra. So let's first check that C is a semi-algebra. So in order to do that, I have to guarantee first that omega belongs to C, but this is clear because omega is just omega 1 times omega 2 times so on. So it's clear since Fj it's a sigma algebra that omega j belongs to Fj, and therefore omega is a cylinder set. So then we need to check that any element, of that C, it's closed under intersections. So if I take two cylinder sets A and B, I have to check that A intersection B belongs to C. Well, but since A and B belongs to C, both A and B are essentially finite sets. So A can be written as A1 times An times omega n plus 1, where Aj belongs to Fj. And similarly, B can be written as B1 times Bn. Of course, here the coordinate may be different. M might be different from N, where Bj belongs to Fj. Here, or let me write it k, and k goes from 1 to m, while j goes from 1 to n. Well, let's assume without loss of generality that n is less or equal than m. So I can just complete here. So I can rewrite a as a1 times an times omega n plus 1 times omega m times omega m plus 1. Now both are ending at the same coordinate, and then check that the intersection of a b is just the intersection of a1 b1 times a2 b2 times an bn, and then bn plus 1 up to bm, since an plus 1 am are equal to omega n plus 1 omega m, and therefore that the intersection of a and b is a cylinder set. We are just what we are doing here is that we are reducing the problem to a finite dimensional problem in m coordinates. So the same argument which proved that in the case of a finite product, the set of rectangles formed semi-algebra, the same argument here gives that the cylinder sets form semi-algebra. And so the same argument shows that if A is a cylinder set, then the complement of A can be written as finite union of cylinder sets. So there exists n, and there exists A1, or let me write it here, A1, AN in C, such that A complement is equal to AJ for J from 1 to n. And here again, I won't give you the details of this proof, but essentially if A is a cylinder set, it depends on the first n coordinates. It can be written as A1, AN. So now if you take the complement of this set, you can just ignore what happens on the last, the coordinates starting from n plus 1, and concentrate on the first n coordinates, and then write that the complement of A1 times A2 times AN can be written as a union of sets of the form B1 times B2 times Bn, where Bn, Bj, it's either Aj or Aj complement, and you have to take at least one of these Bj equal to Aj complement in order to get all. So you have written, if A depends on the first n coordinates, A complement as a union over 2 to the power n minus 1 sets. You take all possible combinations. So maybe let me write that in detail to make it clear. So let me give you a precise proof of this claim. So let's assume that A is a cylinder set. This means that A can be written as A1 times AN times omega n plus 1, omega n plus 2, and so on. Right? This is by definition of a cylinder set. Now I want to consider A complement. So what I claim is that since A depends only on the first n coordinates, I have only to bother on these first n coordinates. And so if I take A complement, what I claim is that A complement it's equal to a union of sets, let me call that B1 sigma 1 times bn sigma n times omega n plus 1, omega n plus 2, and so on, where here sigma 1 it's equal to either plus 1 or minus 1, sigma n it's equal to plus 1 or minus 1. This, what is, so bj 1, so if sigma j it's equal to 1, bj it's aj, while if sigma it's equal to minus 1, bj minus 1, it's equal to aj complement. So we are performing here a sum over two n sets, and I want to remove from this sum the case in which every sigma it's equal to plus 1, because if every sigma it's equal to plus 1, we recover the set A. So this is done over all sigma 1, sigma n, such that if I sum from 1 up to n sigma j, 1 if sigma j it's equal to plus 1, this sum, or let's say minus 1, this sum should be greater or equal to 1. So I want to, with this condition, I'm removing the case in which all sigma j's are equal to plus 1, because in that case all these sets bj's are equal to aj, and therefore I recover the set A. So I leave it to you to check that A complement it's this union. So now it's very easy to check first that for any sigma 1, sigma n, these sets belong to the cylinder sets. And secondly, that all these sets, if you take different sigmas, you get disjoint sets here, and therefore we have written A complement as a finite union of disjoint elements of the cylinder set, and therefore we proved the third property of the semi-algebra. So this shows that the class C of cylinder sets indeed forms a semi-algebra. So now that we have seen that C it's a semi-algebra, let me define a function mu from C to 0, 1. So the values are between 0 and 1 because I'm assuming here that mu j omega j is equal to 1. So let's assume that A it's an element of C. Therefore A can be written as A1 times A2 times An times omega n plus 1, where Aj belongs to Fj. And if mu is such, if A is a set, I will define mu of A as the product from j from 1 to n of mu j aj. So you see aj is an element of the sigma algebra Fj, so mu j aj it's well defined. And here I can, since I'm assuming that mu k of omega k is equal to 1, here in fact I have the product from j greater than n of mu j omega j, but this product is just equal to 1, so I don't write it. So here's the definition. So now we have defined a function in the semi-algebra C, and we know by Kara-Theodori theorem is that if we are able to show that this function it's a sigma additive, then we can extend it in a unique way to the sigma algebra generated by the cylinder sets. So we won't prove that mu is sigma additive in the semi-algebra. What we will do is that we will first extend mu to the algebra, and then we will show that this function it's continuous from above at the empty set, and therefore that it's sigma additive by a theorem that we proved in the beginning of these lectures. So that mu it's additive, it's very simple because we have again we are reduced to a finite dimensional problem, so I will discuss that just to make sure that you understand the notation, and then we will extend mu from this semi-algebra of cylinder sets to the algebra generated by the cylinder sets, and then prove that this function defined on the algebra it's continuous from above at the empty set. So I want to just show that mu is additive on C. So this means that let's assume that A belongs to C and that A1, AK belongs to C, and that A can be written as a finite sum of AJ. Well, but if A belongs to C, A depends only on a finite number of coordinates, so A can be written as A1 times AN times omega n plus 1. And the same thing holds for each of these sets AJ. So AJ can also be written as AJ1 times AJ. But now, of course, the index here might be different. So here I will represent it by NJ times omega n j plus 1, and this is true for j from 1 up to k. Now let me define m as the largest of these values n and nj. So n it's the maximum between n and nj, where j goes from 1, so maybe let me write it in this way, and 1 up to nk. So I will represent A and each of aj as a product up to m. So I will replace, let's say that n is smaller than m, so I'll just replace omega, say n plus 1 by an plus 1, just to have everything going to up to the same index. So A, I'm rewriting it as A1 up to AM up to omega times omega m plus 1, and each of these AJ as AJ1, AJM times omega m plus 1, and this is for j between 1 and k. Now they all, of course, some of these m are equal to omega m, might be equal to omega m, but I don't care. What I have here is that all these sets depend on the first m coordinates, and therefore I have, if I just ignore these the coordinates starting from m plus 1, I have here represented a finite dimensional set as a union of finite union of finite dimensional sets, and therefore, since mu a it's equal to let's say L equal to 1 up to m of mu L AL, and mu AJ, it's also equal to this product. And we have seen, we have seen that these measures on the right-hand side, which are product measures on a finite dimensional set, are sigma additive, not only additive, but sigma additive. We can use the additivity of the measure written on the right-hand side to show that mu is additive. This argument doesn't hold for a countable union of sets. So if instead of I write A not as a finite union but as a countable union, I cannot apply this argument because it might happen that AJ depends on a larger and larger number of coordinates. So I will not be able to reduce the argument to a finite number of coordinates if I have here a countable union of sets. So additivity, it's very easy to show because it follows from the additivity that we proved in the case of a finite product of sets. The countable additivity, it's the sigma additivity, it's more complicated because it might happen that as J becomes larger and larger, AJ depends on a larger and larger number of coordinates, and therefore we need an alternative, a new argument, in order to show this sigma additivity. So up to this point, we introduced C, which is this family of cylinder sets, and we showed that C is a semi-algebra. And we defined the function mu on C by as follows. If A is a set which can be written as A1 times AN times omega n plus 1, then mu A is just the product of mu J AJ. And we have seen that mu defined in this way, it's additive. Now let me denote it by A, the algebra generated by the cylinder sets. So we know exactly what is this algebra. All the sets in this algebra are finite unions of elements of the semi-algebra. So all elements of A of C, or of A, are finite union of cylinder sets. And we know that there exists a unique way in which we can extend mu from C to A. So I will use the same notation to represent this function mu, which is now defined on the algebra generated by these cylinder sets. Right? So we have seen that there exists a unique way. So if a set B belongs to the algebra, B it's a finite disjoint union of cylinder sets, and mu of B will be just the sum of the measures of these sets. So this defines mu on A. It's an extension, and it's the unique extension of the function mu defined on the semi-algebra. And all the argument will be to show that this function, mu defined on the algebra, it's continuous from above at the empty set. Note that mu takes only values between 0 and 1, because we are assuming that mu of omega j it's 1. So all these products, all these values are between 0 and 1, and therefore this product belongs to 0 and 1. So in order to show that mu is continuous from above at the empty set, we'll take a sequence denoted by AJ of elements of the algebra, decreasing to the empty set, and we have to show that mu of this AJ converges to 0. So theorem, so mu it's continuous from above at the empty set. So mu, which is defined, so remember that this function mu, it's defined on the algebra. So this is what we want to prove. And in order to prove that, we will prove an identity which will be very useful. To prove this identity, so what we are doing here is what we are starting. So we are constructing a function which is defined on omega 1 times omega 2 and so on, which we denoted this set by omega. We could also consider the space starting from omega 2 times omega 3 and so on, which we denoted by omega 2, right? And we could define a function or a measure on these sets. So we could start by considering the cylinder sets of the set omega 2, which let me represent them by C2, and the algebra generated by these cylinder sets, which I'm representing by A2. And as we did for the set omega, construct a function defined in A2, and I will represent this function by nu2. So nu2, it's exactly the function nu, but instead of being defined in omega 1 times omega 2, it's defined in omega 2 times omega 3, and so on. Right? So just to make sure that you are understanding, let's consider set E in, let's say, C2. So if E is in C2, this means that E can be written as a set which I will represent by E2 times E3 times EM times omega m plus 1. Note that I'm starting here from 2 just not to mix the index, and the definition of nu2 of this set E would be just the product from j from 2 up to m of mu j ej. So this is the definition nu2 of set E given by that, and you can extend that to the algebra. So this is what I understand by the measure nu2. So nu2 is defined in the cylinder sets, or the algebra generated by the cylinder sets of omega 2, and in general I will have I will define nu k, which will be defined in the cylinder sets or in the algebra generated by the cylinder sets of nu k. And this is for k greater or equal than 2. Right? So in the same way as I introduced nu2, I could have defined nu k, which is defined in the infinite product omega k, which starts from omega k plus 1, and so on. It's defined first in the cylinder sets of omega k, and then can be extended to the algebra generated by the cylinder sets. So this is what I will understand by nu k. So these are just notation. And why am I introducing this notation? It's for the following reason. Take a set A first in the cylinder set A, and I will represent, so A, it's given by let's say E1 times En times omega n plus 1, where Ej belongs to Fj. Now, for x in omega 1, or x1 in omega 1, so let me take a point in omega 1, and I want to define the section at x1 of the set A. So AX1 will be the section of the set A at x1. So this set will be a subset of omega 2, which, remember, it's omega 2 times omega 3 times so on. So what is the definition of this section? Well, we define a section when A it's a finite dimensional set, but since A it's a cylinder set, it's essentially a finite dimensional set. So AX1, if A it's a cylinder set, so if A is represented as E1 times E2 times En and so on, well, what is the section? Well, either x1 belongs to E1. So if x1 belongs to E1, so let's say that if n is equal to 2, just to have a picture, so A will be E1 times E2 times omega 3, omega 4, and so on. So we could represent so let me write that as E2 times omega 3. So if x belongs to E1, the section at x will be just E2 times omega 3. While if x does not belong to E1, the section will be the empty set. So the same thing can be extended to a cylinder set, in the sense that if x it's an element of E1, then the section at x1 of the set A is just E2 times E3 times En times omega n plus 1. While if x1 does not belong to E1, then the section will be just the empty set. So this is the section at x1 of the set A, which, as you can see, it's an element of, it's a subset of omega 2, it's an element of C2. And as we defined a section of a cylinder set, if A now it's an element of the algebra, therefore it will be finite disjoint union of such elements, I can also define this section by in a similar way. A will be the union, so I'll just take the union of these sections. Okay, so remember that a section of a union is just the union of these sections. So here's the definition of a section. So my claim is the following. If you take A in a cylinder set, then if I compute mu of A, so mu it's defined in the algebra, it's defined in the cylinder set, so that's fine. What I want is I will take mu2 of AX. So remember, A it's a cylinder set. It's a cylinder set. AX it's the section at x of the set A, which is a subset of omega 2. It's in fact a cylinder. So let me write that. For all x in omega 1, AX it's a cylinder set in C2. And therefore, mu2 of AX it's well defined. And this now it's a function of x. What I claim is that as a function of x, so the function which at x associates mu2 of AX is measurable. It's F1 measurable. So it belongs to 0 and 1. So I can integrate this measurable function with respect to mu1, because, well, this function as a function of x, it's f1 measurable, so I can integrate it with respect to mu1. So let me just represent that in this way to remember that we are integrating here with respect to x. And my claim is that we have this identity, so that mu of a, it's in fact equal to the mu2 measure of the section ax integrated with respect to mu1. So, and it's implicit in this identity that the function which associates to x the measure of the mu2 measure of the section at x of a, it's f1 measurable. So let's prove that. So let's take A in a cylinder set, as a cylinder set. So A can be written as E1 times En times omega n plus 1. So we have seen that Ax, if I take x in omega 1, this is either equal to E2 times En times omega n plus 1. This if x belongs to E1, and it's the empty set if x does not belong to E1. So mu2 of Ax, it's always well defined, because it's either 0 if x does not belong to E1, and if it's mu2 of this cylinder set if x belongs to E. So mu2 of Ax, it's equal to, well, 0 if x does not belong to 1, and if x, so let me here introduce the indicator of the set E1, right, because it will be 0 if x does not belong to 1, so let me introduce this indicator, which is 1 if x belongs to E1 and 0 otherwise. And now, what is mu2 of this set? Well, mu2 of this set is just the product from 2 to n of mu j ej, right? So here I want to compute mu2 of Ax. Mu2 of this set, which is Ax, in case x is in E1, mu2 of this set is just mu2 of E2 times mu3 E3, mu n En times 1. So this is exactly what I wrote here. And in particular, you see that as a function of x, mu2 of Ax is a simple function. It's a constant times the indicator of the set E1. So it's not only integrable or measurable, but it's in fact a simple function. So now we can, so this proves the first assertion is that, well, this function as a function of x, it's measurable. In fact, it's more than measurable. It's a simple function. And now we can integrate this function with respect to mu1. So let's integrate the function mu2 of Ax d with respect to mu1. As a function of x, let's integrate it with respect to mu1. So this is the integral of this simple function. So this is a constant, it gets out from the integral. Then we integrate this simple function, but the integral of this simple function is just mu1 of E1. So this is equal to mu1 E1 times the product from 2 to n of mu j ej. And we recover here the product from 1 to n of mu j ej. But now if you remember that A, it's E1 times E2 times En times omega n plus 1, this is just mu of A. So this proves that indeed mu of A, it's equal to the integral with respect to mu1 of mu2 of the set AX, which is the formula I wrote here. So this proves the claim, and this identity will be very important in the proof that the measure mu it continues from above at the empty set. Okay. So let me just make a remark before we proceed. I want to extend this identity to sets A in the algebra. And this, I will do that by linearity. So what I claim is that the same statement holds for elements of the algebra. And why is that? Well, assume that A, it's an element of the algebra. Therefore, A can be written as a finite union of elements AJ, where AJ are cylinder sets. And what I claim, and I leave it to you to check, that if I take now the section at X of A, so this is, well, A by definition, it's finite union so I take this finite union of cylinder sets, and I take the section at X of this finite union. And what I claim, and I leave it to you to check, well, we did that already in the finite dimensional case, is that this is equal to the union of these sections. Okay? So this is what I claimed a few times before. If you take a set A, which is a finite union, you take its section at X. The section at X is the union of these sections. So by using this identity, we can extend this identity to the algebra. And how we do that? Well, so mu2 of AX d mu1, it's equal, by this identity, as the sum of these sections. But since these sections are all disjoint, the measure of the union is the union of the measures. So this because we proved already the additivity of mu2. Okay, so remember that we proved the additivity of these measures. So we can use here the fact that it's additive. Now, it follows from this identity that this function it's measurable because this function it's the sum. We proved each AJ it's a cylinder set, so I erased it, but let me recall that since A is an element of the algebra, it can be written as a finite union of elements of the cylinder sets. And we proved already that these functions here are measurable with respect to f1 in X. Therefore, the sum, it's measurable, and therefore, this function, it's measurable. Now, we can use the fact that the integral of a sum, it's the sum, the linearity of the integral. So we can exchange the integral with the sum. Once we exchange the integral of the sum, so let me continue here. Once I exchange, I have that expression, it's equal to a sum from 1 up to n. of the integral of mu2 ajx d mu1. But now I can use this identity for cylinder sets because aj is a cylinder set. And therefore, this identity will tell me that, well, this integral is in fact equal to mu of aj. And since A is equal to the union of mu of j by the additivity of mu, which I proved already, this is mu of A. So this proves that mu of A is indeed equal to the integral of mu2 ax d mu1x, which extends that identity to elements of the algebra. So now we can start to prove that mu is continuous from above at the empty set. So to show that, so this is the proof of the continuity. So to prove that it's continuous, we consider a sequence an of elements of the algebra. We assume that an decreases to the empty set, and we have to prove that mu of an converges to 0. Okay? So we will proceed, in fact, by proving it converges, which means that we'll consider a sequence an in the algebra, an decreasing. We assume that mu of an, so that there exists an epsilon positive, such that mu of an is strictly greater or equal than epsilon for all n, and we will show that the intersection of an is non-empty. So we will find a point in the intersection of an. So this is our goal. We consider a sequence of elements in the algebra. This sequence is decreasing in the sense that an contains an plus 1. We assume that the measure of an are bounded below by a strictly positive constant, and we will prove that the intersection of the an's is non-empty. So we will find a point, and a point here it's an infinite sequence which belongs to all sets an. So let me prove that, and for that we will strongly use this identity. So let's consider this sequence an, and let me take an, well, the section at x of the set an. So anx, an it's an element of the algebra, so anx it's an element of the algebra A2. For each x in omega 1, anx it's an element of the algebra A2. In this algebra A2, the measure nu2 is well defined. So I have nu2 of anx. So this, it's a number between 0 and 1. And I will define Bn as the set of points x such that nu of anx is larger or equal than epsilon over 2. Okay, so these points x are all elements of omega 1. Okay, so remember, an it's an element of the algebra. Therefore, this section at x for any point x in omega 1, it's an element of the algebra A2. Therefore, nu2 is well defined. And more than that, the function which at x associates nu2 of anx, it's measurable. And here I'm taking all points x for which this quantity is larger than epsilon over 2. So this is an element of f1. Right? Because this is a measurable function, and this is the inverse image of the interval epsilon over 2 plus infinity of a measurable function, so it's an element of the sigma algebra F1. So these sets Bn all belong to F1. And more than that, Bn are decreasing, because since An is decreasing, if I know that new An plus 1, so the section at x plus 1 at x, if the section at x of the set An plus 1 has measure larger than epsilon over 2, since An plus 1 is contained in An, the section at x of An has to be also larger or equal than epsilon over 2. So the sequence Bn, which are elements of F1, are decreasing. And now we will use that identity to obtain information about the measure of the sets Bn. So I just rewrote in this blackboard the identity we proved for any element of the algebra, that mu of A is given by this integral, and the definition of the set Bn. So it's all points x in omega 1 for which the n2, nu2 measure of A and x, it's larger or equal than epsilon over 2. And now let's recall that this sequence An, by assumption, has measure mu measure greater than epsilon. So epsilon, it's less than or equal to mu of An. And by this identity, mu of An, it's equal to nu2 of Anx d mu1 x. And here is n. Fine. So let's now divide this integral in two pieces, one which is in Bn and the other one in Bn complement. So I'm rewriting this integral as an integral over the set Bn and one piece over the set Bn complement. Bn complement x. Right, so I'm dividing this integral in two pieces. Either x belongs to Bn, which is that one, or x belongs to Bn complement, which is this one. So here I'm not writing nu2 of A and x. So let's see what happens in these two sets. Well, on the set Bn complement, which is this set, I know that this function, so I'm looking at this piece. If x belongs to Bn complement, so it doesn't belong to Bn, this means that the measure of this section is bounded by epsilon over 2, so that this expression is bounded by epsilon over 2. So since the integrals are monotone, this means that on the set Bn complement, so let me write it here, Bn complement, this expression is bounded by epsilon over 2. So this integral is less or equal than epsilon over 2 times the measure mu1 of Bn complement. So this is the estimate of the first piece. Then there is a second piece which is on Bn. Well, on Bn, the only thing I will use is the fact that this measure is bounded by 1. We know that nu2, whatever the set, it's always less or equal than 1. So this is the inequality I'm using, and so what will remain, it's mu1 of Bn. So plus mu1 of Bn. Okay. So we proved that mu of An, which is given by this integral, it's in fact bounded by epsilon over 2 mu1 of Bn complement plus mu1 of Bn. And mu1 of Bn complement, it's mu1 of omega 1, which is 1, minus mu1 of Bn. So let me write the first term as the total measure of the set omega 1, which is 1 by assumption, minus the measure of Bn. And then the second, I will just leave it as mu1 of Bn. And let's see what we have. We have that epsilon is less or equal than epsilon over 2 times this expression plus this measure. So if I take epsilon on the other side, what I get is that epsilon over 2, it's less or equal. So I have here epsilon minus epsilon over 2. And then I have mu of Bn, which is multiplied by 1 minus epsilon over 2. And this is less than mu1 of Bn. Mu1 of Bn. So we proved that the sets Bn have all mu1 measure larger than epsilon over 2. So this is the conclusion of this estimate, which is based on this identity. So I will erase everything and I will just keep the fact that mu of 1 of Bn it's larger or equal than epsilon over 2. So we proved that mu1 of Bn it's larger than epsilon over 2. Well, but Bn are elements of the sigma algebra F1 and they are decreasing. So now I can use the fact that mu1 it's a measure to claim that the intersection, so I have here a sequence of sets which is decreasing and whose measure it's bounded below by a strictly positive constant. This implies, because mu1 it's a measure, that the intersection of Bn it's non-empty. But now let's check what is the intersection of Bn. So if I take a point x1 in this intersection of Bn, I know I just proved the existence of at least one point in the intersection of Bn, because we just proved by using the fact that mu1 is a measure that this intersection is non-empty. If I take a point x1 in the intersection of Bn, this means that for that point, since it's in the intersection of Bn, this means that nu2 of an x1 it's larger than epsilon over 2 for all n. Okay. So now let's see what we proved up to now. We started with a sequence an which was decreasing and such that mu of an was larger than epsilon. And by this argument we obtained a point x1 such in, so x1 it's in omega 1, right? We obtained a point x1 in omega 1 such that if I take the section at x1 of the sets an, its nu2 measure it's bounded by epsilon over 2 for all n. This section anx are elements now of omega 2 and they are decreasing. So we passed from a sequence which was defined in omega, so these sets an were subsets of omega. By considering the section at x1, we obtain now subsets in omega 2, which have exactly the same properties of the original set. They are decreasing, these sections are decreasing. Their measure are bounded below by a strictly positive constant. They are bounded by the new 2 measure are bounded below by a strictly positive constant. And now they are elements of omega 2. So we can iterate. What I want to do now is iterate this relation in order to construct a family of sections with this property. So let me formalize that in a new blackboard. So what did we do? We started with a sequence an of sets an, which are elements of the algebra. Then so let me maybe write that an, it's an element of the algebra. They are decreasing, and their new measure is bounded below by epsilon. From that, with our argument, we constructed a point x1 in omega 1, such that these sections an are now elements of the algebra A2. These sections are decreasing, and their new 2 measure, it's bounded below by epsilon over 2. What I claim is that if now we repeat the same argument, we can iterate this procedure and obtain at step k that there exists a point x1 xk which belongs to omega 1 up to times omega k, and such that an x1 xk belongs to the algebra a k plus 1. They are decreasing, so an x1 xk contains an plus 1 x1 xk, and the new k plus 1 measure of an x1 xk, it's larger or equal than epsilon over 2 to the power k for all n. Right, so by replacing mu by mu2 and an by an x1, I can just iterate the argument to construct these sequence of points x1, x2, xk. What I claim is that by iterating this procedure k time, what you obtain, it's a point x1 xk in omega 1 times omega k with these properties. And now my claim to conclude the proof of the continuity from above is that the sequence x1, x2, and so on, so this point, which is a point in omega, in fact belongs to the intersection of the an. And so if I prove this claim, I would have proved the continuity from above, because I found a point x1, x2, x and so on in the product omega 1 times omega 2, so in our set omega, which belongs to all sets an. So we proved that the intersection of the sets an is non-empty because we found a point which belongs to the intersection. So this is what I need to prove, and I will use what I wrote here to prove that claim. And to prove that claim, so we will use the fact that ANs are elements of the algebra. So to show that this point belongs to this intersection, I have to show that this point x1, x2 belongs to AN. So I fix n, and I want to show that this point belongs to the set AN. Well, but AN, it's a, so AN, so here's a mistake, it's AN, n is above. So AN, it's an element of the algebra. But elements of the algebra are union of cylinder sets, which means that they depend only on a finite number of coordinates. So my claim is that there exist, since AN is an element of the algebra, there exists K, or let me call it maybe M, with the following property: if y1, y2 belongs to AN, so this is a property of elements of the algebra, right? It's not a property of AN. I'm just using here the fact that A is an element of the algebra. So what I claim is that there exists M with the following property: if y1, y2, so if a sequence of points, an infinite sequence belongs to AN, and if if I have another point z1, z2, such that zj is equal to yj for 1 up to m, then z1, z2 belongs to AN. And this is if and only if, right? So this means the following: if two sequences coincide up to the coordinate m, one of them belongs to AN if and only if the other one belongs to AN. So this is clear for elements of the semi-algebra. So if A, so let me skip the index n. So if A is equal to E1 times E2 times E, let me call it R times omega R plus 1. So you see a point belongs to A if and only if the first coordinate is in E1, the second in E2, and the rth it's in ER. In particular, if two sequences coincide up to the coordinate R, so if I take M equal to R, so if they coincide up to the coordinate R, one of them belongs to the set A if and only if the other one belongs to the set A. So I proved this claim for elements of the semi-algebra, but the elements of the algebra are finite union of these elements, so you can extend the argument to the algebra. So now let's apply this statement to AN. So AN, it's an element of the algebra, so I know that there exists such an M. So there exists an M for which if two sequences coincide up to the mth coordinate, one of them belongs to AN if and only if another one belongs to AN. Well, I know that we proved by, so let me fix that M. We proved that these sequences are all non-empty because their measures are strictly positive. So since this measure is strictly positive, I know that AN x1 xk is not empty. Okay? So for any k, I found a point x1 xk such that this measure is larger or equal than epsilon to 2k. In particular, this set is not empty. So I know, applying that to taking k equal to m, I know that AN x1 xm is non-empty, right? By taking k equal to m in this step. Well, if So this means that this section is not empty. So this means that there exists ym plus 1, which ym plus 2, and so on. So a sequence ym plus 2, ym plus 1, ym plus 2, ym plus 3, and so on, such that which belongs to this set. So which belongs to the set, the section at x1, xm of an. But this means but since this sequence belongs to this section, this means that x1, x2, xm, ym plus 1, ym plus 2, and so on belongs to an. Right? If I have a point which belongs to the section, this means that if I complete this section with that coordinate, this point belongs to the set an. So I proved the existence of a point which belongs to an. But now, what is the coordinate m? Well, the coordinate m was chosen to have this property. If two points coincide up to the coordinate m, then one of them belongs to n if and only if the other one belongs. But the sequence x1, this sequence, and the sequence x1, x2, x3, and so on, well, they coincide up to the coordinate m. So since this point belongs to an, that point belongs to an, and this is exactly what we wanted to prove. We wanted to prove that the sequence x1, x2, x3 belonged to an. And this is what we proved, and therefore we have shown that the sequence x1, x2, x3 belongs to the intersection of an, proving that mu it's continuous from above at the empty set, and therefore that it is sigma additive, and this concludes the proof, the construction of the measure on the product space, because now we can just apply Carré-Theodori theorem. So let me just conclude with this remark. Right. So we just proved that mu is continuous from above at the empty set, and this guarantees therefore that mu it's sigma additive and well, therefore we can just apply the Carré-Theodori extension theorem to extend mu. So this allows us to extend mu to the sigma algebra, which I'm representing by F, which is the sigma algebra generated by the cylinder sets. So we constructed a measure on the sigma algebra generated by the cylinder set, which is an extension of the function defined on the cylinder set. So remember that mu, what characterizes mu is that mu of the set E1 times En times omega n plus 1. If E1 belongs to F1, En belongs to Fn. This is just mu j of Ej from 1 to n. And this is why we call mu as the product measure, because mu, the measure of a cylinder set, is just the product of the measures, and therefore this measure we will call the product measure, and this sigma algebra the product sigma algebra on this countable product of spaces. So this was the goal of this lecture.